Hadrons. The name comes from the Greek hadros, meaning thick or bulky. They are the particles that experience the strong force and the weak force, though leptons also experience the weak force. They're made up of combinations of quarks. There are two types of hadrons, baryons and mesons. First, to look at the baryons. These consist of 3 quarks. The proton is the only stable baryon. All the others, including free neutrons, will eventually decay into a proton. The neutrons inside a nucleus are stable. This table summarizes the properties of charge and baryon number for the 6 quarks. The charge is given as a multiple of the magnitude of the charge on the electron of 1.6 times 10 to the minus 19 coulombs. The antiquarks simply have the opposite charge and baryon number to their quark counterpart. So for example, the anti-down quark has a charge of plus 1/3, a baryon number of minus 1/3. Just to look at a few examples of baryons. First, the proton, which consists of 2 up and 1 down quark. The charge will be plus 2/3 for the first up quark, plus 2/3 for the second up quark, minus 1/3 for the down quark, giving a total charge, as expected for the proton, of plus 1. Baryon number is simply 1/3 plus 1/3 plus 1/3, giving a baryon number of 1. The neutron consists of 2 down and an up quark, so the charge will be minus 1/3, minus 1/3, plus 2/3, giving the familiar charge of 0 for the neutron. Baryon number again is 1/3 plus 1/3 plus 1/3, giving a baryon number of 1. The antiproton is the same as the proton, but with each quark replaced by the antiquark. So it's an anti-up, anti-up, anti-down. This gives a charge of minus 2/3, minus 2/3 plus 1/3, or a charge of minus 1, the opposite charge to the proton. Baryon number, minus 1/3, minus 1/3, minus 1/3, giving a baryon number of minus 1. As you might expect, all baryons have a baryon number of plus 1, antibaryons having a baryon number of minus 1. Now to look at mesons. Mesons consist of a quark-antiquark pair. Here again is the table of charge and baryon number for quarks for us to refer to. Now to look at a few mesons. First, the pi minus, one of the pions. This consists of a down anti-up pair, and so the charge is minus 1/3 for the down, minus 2/3 for the anti-up, giving an overall charge of minus 1, hence the superscript of a minus sign. Baryon number, plus 1/3 for the down, minus 1/3 for the anti-up, giving a baryon number of 0, the same as all mesons. The K0, or anti-K0 here, one of the kaons, consists of a strange anti-down quark. Charge is minus 1/3 for the strange, plus 1/3 for the anti-down, giving an overall charge of 0, hence the 0 superscript, and a baryon number of plus 1/3, minus 1/3, 0, like all mesons. Conservation rules. Charge, baryon number and lepton number are conserved in all interactions. If any one of these is not conserved, the event is not possible, and is not seen. First to look at the familiar case of beta minus decay, in which a neutron becomes a proton plus a beta minus particle or electron plus an electron anti-neutrino. Well, the charge, the neutron has a charge of 0, the proton a charge of +1, the beta minus a charge of -1, and the electron antineutrino 0 charge, and naught does equal +1 -1 plus naught. So that is okay. Baryon number. Well, the neutron has a baryon number of 1, the proton a baryon number of 1, the beta minus and the electron antineutrino both have 0 baryon number, and so that is okay. Lepton number. Well, the neutron has 0 lepton number, as does the proton. The beta minus has a lepton number of +1, it is a lepton. The electron antineutrino has a lepton number of -1, it is an anti-lepton. And naught is equal to naught plus 1 minus 1, so that is okay. It has to be okay, beta minus decay occurs. In beta minus decay, a down quark changes flavour to become an up quark. So we go from down, down, up of the neutron to up, up, down of the proton. This is a weak interaction involving the weak force. Now to look at a few other interactions. In this case, a pi minus, one of the pions, plus a proton becomes a pi naught, another pion, plus a neutron. Just to check, this obeys the conservation laws. For charge, the pi minus has a charge of -1, the proton a charge of +1, the pi naught 0 charge, and the neutron 0 charge. So this is 0 on either side, which is okay. Baryon number. Well, the pi minus has 0 baryon number, the proton a baryon number of 1, the pi naught a baryon number of 0, and the neutron a baryon number of 1. So this is 1 on both sides, which is okay. Lepton number. Well, in this case, everything on either side has 0 lepton number. There are no leptons involved here, so that also is okay. So this interaction is allowable by the conservation rules and is seen. In this example, a proton becomes a pi plus plus a gamma ray. In terms of charge, the proton has a charge of +1, the pi plus a charge of +1, the gamma ray is neutral, so in terms of charge conservation this is okay. Baryon number. Proton has a baryon number of +1, the pi plus 0 baryon number, the gamma ray 0 baryon number. So this does not balance, it is not okay, meaning we break the conservation laws, this interaction cannot occur. Lepton number. Well, again, all these are not leptons, and so in terms of lepton number this is okay. However, breaking one conservation law means the interaction is not possible. In this case, a proton becomes an anti-electron or a positron plus a pi naught. Charge. The proton has a charge of +1, the positron a charge of +1, and the pi naught is neutral. so this is OK. Baryon number. The proton has a baryon number of 1, the positron and the pi naught both have 0 baryon number, so this violates the conservation of baryon number. It is not OK, the interaction is not seen. Lepton number. Well, now we have the proton with 0 lepton number. A positron is an anti-lepton and so has a lepton number of -1, and the pi naught has 0 lepton number. So this also violates the conservation of lepton number and is not OK. Now to look at another property, that of strangeness. Some interactions which appeared possible according to the laws of conservation of charge, baryon number and lepton number were never actually observed to occur. This led to the discovery of another conserved property which became called strangeness due to the strange behaviour of some particles. The strange quark has a strangeness of -1, while the anti-strange quark has a strangeness of +1. All other quarks have 0 strangeness. Hadrons experience the strong and weak force. Strangeness is conserved in strong interactions, but not in weak interactions. Weak interactions involve a change of quark flavour, such as when a strange quark decays into an up quark. In this interaction, a pi plus or pion plus plus a neutron becomes a lambda naught and a kaon plus or k plus. Looking at charge, the pi plus has a charge of +1, the neutron is neutral, the lambda naught is neutral, and the k plus has a charge of +1. So in terms of charge conservation, that's OK. Baryon number. The pi plus has 0 baryon number, the neutron baryon number of +1, the lambda naught a baryon number of +1, and the K plus has 0 baryon number. So, in terms of conservation of baryon number, that is OK. Lepton number. Well, none of these are leptons, so that is OK. And finally, strangeness. The pi plus has 0 strangeness, as does the neutron. The lambda naught has a strangeness of -1. It contains a strange quark. The K plus has a strangeness of +1. It contains an anti-strange quark. So we have conservation of strangeness, and the interaction is therefore OK. In any questions, you will be given the charge, baryon number, lepton number and strangeness of any particles involved. You won't be expected to remember these details, however you will be expected to be able to work out whether the interaction is possible by laying out what the charge, baryon number, lepton number and strangeness of the interaction is, to decide whether or not it can happen.